This is a momentum problem, and what we're trying to do is find the net momentum flux in the x direction for a unit width. And we're assuming that rho is constant, and we're given the picture below with which to determine our velocities. So if we write our momentum equation, there are three control surfaces. Control surface 1, rho u1 v1 dot n dA1 plus over control surface 2, rho u2 v2 dot n dA2 plus over control surface 3, rho u3 v3 dot n dA3. So the first thing that we see is, since this is in the x direction and the velocity over here at 2 is only in the y direction, that this goes to 0. So let's start with the first term. Our control surface is going to be area 1. Rho is constant. So what is U1? Well, if you take a look up here, right, and this is our V1, what we're looking for is the component in the x direction. So that's just going to be V1 cosine of theta. If you take a look at the direction of it, it's negative in terms of our x-axis. So our u1 is going to be minus v1 cosine of theta. Next, we have to find v1 dot n, and since it is entering the control system, the normal is in the opposite direction of the velocity. So this is minus v1. Since our velocities are not a function of any part of the area, we can take everything out of the integral, and our first term is going to be rho v1 squared, the two negatives make a positive, cosine of theta times a1. So now let's take a look at 3. And one of the things that you see is that the velocity profile is not uniform. It is a function of y, and we have to figure out what the actual function is. So our v2 is going to be some linear function such that my plus b equals v2. So we know at y equals 0, v equals 0, just from the picture. At y equals a, v equals v max. So, and actually this should be 3, our v3 is going to be v max divided by h times y, because we have two equations, two unknowns. So, since v3 is v max y over h, we need to find u3, and if you notice, it's in the negative direction, so that's minus v max h over y. Then v3 dot n is going to be positive because it is exiting the volume, so this is v max h over y. Notice we don't have any thetas or anything like that because the velocity is only in the x direction. So here the velocity is a function of y, so we have to put it or keep it in our integral. So rho is constant, we can pull it out. We are going to integrate from 0 to h minus, because we got that minus from u3, v max divided by h times y squared w, that's our unit width, dy. So this term here is our dA3. And so when we do the integration, we come out with rho w v squared max times h over 3. And finally, we combine the two terms, r sub x equals rho v1 squared cosine theta a1 minus, and we have to remember to keep that minus sign in there, rho w v max squared h divided by 3.